Hello, everybody. Welcome to today's current seminar. Today we have two speakers, two talks. Our first speaker is Vivek Oommen. He will be giving a talk on learning turbulent flows with generative models, super resolution forecasting, and sparse flow reconstruction. Vivek is a fifth-year PhD student working with Professor George Karniadakis at Brown University. He works with operator learning and physics-informed machine learning to develop computationally efficient models of physical systems. Prior to joining Brown, he completed his bachelor's in mechanical engineering and a master's in data science from the Indian Institute of Technology, IIT Madras. With that short introduction, the floor is yours and you can start your presentation.
Thank you, Nazanin. This work was done in with the help of Dr. Siavash, Aniruddha, Zicheng, and Professor George Karniadakis. So let me just dive in. So why do we need a new approach for modeling spatio-temporal dynamical systems? So we already have classical solvers like the finite element volume or spectral element methods. They already offer high fidelity solutions, provide convergence guarantees, and offer error control. But when you have a new initial condition or boundary condition or new observation, you would have to rerun the entire simulation. Also, the stability requirements and the mesh refinements requires each simulation to be very expensive. So applications that require real-time inference cannot use them directly if there is a new initial condition or boundary condition present. So this is why recently we saw the emergence of neural operators where we can predict new scenarios without retraining. So this facilitates real-time inference in control problems or many different types of problems where it is required. But there's a drawback. It suffers from spectral bias. That is what I'm going to talk about today. So what exactly is spectral bias? Spectral bias is the difficulty in learning high frequencies, while the low frequencies can be easily learned. So here's a toy problem to demonstrate spectral bias. So let us say there is a function sine 2 pi x plus 0.1 times sine 2 pi times 32x. And let's say I want to train a multi-layer perceptron or a fully connected neural network to approximate this function. Let's see what happens during the course of training. So the neural network quickly learns the low frequency component or low wave numbers fast, but it won't be able to learn the high frequency content at all. If you look at the energy spectrum, that is even more clear. There is a non-trivial energy at high wave number, which the neural network is not able to approximate correctly. This is the spectral bias. Why is this important? Because several physical systems exhibits a slow decaying energy spectrum. And we find that neural networks by itself have a hard time approximating these systems. For example, if you look at turbulence, it's another system that exhibits slow decaying energy spectrum. On the left, you see the energy spectrum that decays, and the screenshot is taken from the turbulent flows by Poe. And here is a visualization of Schlieren images of an impinging jet. So what exactly happens when you try to train a neural operator on a multi-scale system like the impinging jet that exhibits slow energy decay? This is what happens. On the left, you see the ground truth, and on the right, you see the neural operator's prediction. So you see it is greatly over-smoothed. You see the dominant features of the shocks and the changes over here. The lower modes are correctly captured, but the high frequency content is absolutely missed. Like the neural operator is not able to learn the high frequency content. If you look at the energy spectrum, that is even more visible. So let's consider this as a critical wave number Kc. All the wave numbers less than this critical wave number Kc are accurately modeled by the neural operator. But when K is greater than Kc, the predictions are less accurate, or these frequencies are underrepresented. So why does this happen? So we investigate how the neural operator is trained to understand why this is happening. So conventionally, we train a neural operator to minimize the mean squared error or an L2 error between the true state and the predicted state in a data-driven sense. So here V of X represents the true output function, and G theta represents the neural operator parameterized by parameters theta that takes U as the input function. And by Parseval-Planger identity, we could represent the same loss function in the frequency domain. Here you can see the dx is changed to dk corresponding to the frequency. So it's the integral, instead of the integral over the spatial domain, we have the integral over the frequency domain. And we can split this integral into subdomains in the frequency domain, where k0 is lesser than k1 is less than k2 up to kn for a sufficiently large n. Now, let me call the first term, which is the integral in the frequency domain from k0 to k1 of the as the term 1 and this as term. So when we are dealing with systems like turbulent flows that exhibits a slow decaying energy spectrum, term 1 becomes much greater than term 2, which is much greater than term n, like in a logarithm. So who is the culprit? As you see here, this is just to let you know, this is the log scale. So when you train the neural operator to minimize like an L2 based loss function, that becomes the culprit. And this causes the lower frequencies or wave numbers to be overrepresented while the network remains oblivious or it underrepresents the high frequencies. So it's unable to penalize the errors at high wave numbers. So in this work, we try to explore if leveraging generative models could help address this limitation of neural operators. So we consider 3 turbulent flow problems where a vanilla neural operator fails. 1, super resolution of the impinging jet that I showed earlier in space and time. So it's a spatiotemporal super resolution problem we are dealing. Then we try to forecast the systems, which is given the historical states, can you predict the future states? Then we check if we can reconstruct the full flow field given sparse velocity measurements. So first, let us take a look at the task 1, which is the spatiotemporal super resolution. So the case here is again, as I said before, the Schlieren visualization of an impinging jet at Mach number equal to 1. Each snapshot is separated by the sampling interval tau equal to 4.76 microseconds. And we actually had 1,000 snapshots at hand, out of which we used 800 for training, 100 for validation, and 100 for testing. Problem setup, given a low resolution, low frame rate input. So here, as you see, the state as you see in the input is spatially subsampled by a factor of 8 and temporally subsampled by a factor of 4. So given a low resolution, low frame rate input, can you accurately reconstruct the high resolution, high frame rate output? That is what we try to investigate here. So our approach, we consider 3 main approaches. 1, the conventional or vanilla neural operators trained to minimize the L2 error, which takes in the low resolution, low frame rate states at t plus tau and t plus 5 tau as the input. And it tries to estimate the high resolution, high frame rate states at t plus tau, 1, 2 tau, 3 tau, 4 tau, all the way up to 5 tau as the output. This is where we saw the neural operator suffer from spectral bias. The results you already saw. An alternate route could be the state estimated by the neural operator can be super resolved using a generative model. So this is what it looks like. Each state is time independently super resolved using this generative model to get a high resolution, high frame rate output. The third option is adversarial training a neural operator, which is just we modify how we train a neural operator by training it adversarially against a discriminator. So let me explain what exactly I mean by adversarial neural operator. Again, during the vanilla neural operator training, I tried to minimize the loss, which is the L2 error between the target function and the neural operator's prediction. But when I train a neural operator adversarially against a discriminator, let me just first call the neural operator's prediction as UF, which corresponds like a fake state, because it's not the real state, it is a state estimated using the neural operator. We try to make the neural operator fool the discriminator. So this is the generative loss, which enables the neural operator to learn the high frequency components. So here we have a discriminator D, And we are trying to train the neural operator to estimate states that a discriminator cannot distinguish from the actual real states from the Schlieren image, so Schlieren photography. So overall, instead of training a vanilla neural operator by minimizing just the L2 error, this is what we do. We minimize the reconstruction loss, which is similar. It's like an L1 norm. Then we have the adversarial loss or the generative loss, where we try to fool the discriminator by making it think the neural operator's prediction is the real state. And we have a perceptual loss, where we try to minimize the error between the states projected using a pre-trained neural networks. So instead of minimizing L in an adversarial NO, we try to minimize L adveno. And after each weight update of the neural operator by minimizing L adveno, we also update the discriminator by minimizing this loss, which essentially tries to correctly distinguish the states estimated using a neural operator and the real state coming from the Schlieren imaging techniques. So it's the neural operator is adversarially trained against a discriminator. I hope this makes sense and you're able to follow. And feel free to interrupt me and ask me questions in between if you have any questions. So here we see the results. In task 1 with super resolution, this is the ground truth, the neural operator predictions with the over-smoothed states, and the predictions using the adversarially trained neural operator plus a variational autoencoder, neural operator plus a GAN or a generative adversarial neural operator, and a neural operator plus a diffusion model. And if you look at their energy spectrums, you'll see the neural operator has the worst energy spectrum, followed by NO plus VA, followed by GAN diffusion model, and the adversarially trained neural operator. So we see that at least the bottom row sufficiently addresses the neural operator spectral bias by reconstructing the high frequency component. So now how do we decide which is the best model? To this, we check the error and the cost associated with each of these models. So here we plot the error in the energy spectrum against the inference cost in terms of gigaflops. So as you see, the neural operators have neural operator has a very high energy spectrum error because of the spectral bias as discussed earlier. Then comes NO plus VA, and NO plus GAN, NO plus diffusion model, and adveno has very low energy spectrum error. But the thing is, because the adversarial neural operator achieves like a 15 times lower energy spectrum error than NO, but at same inference cost as the neural operator. While the NO plus GAN and diffusion model requires additional computations, especially diffusion model because it requires denoising iterations to estimate the super resolved states for each time step t. We further look more closely into the errors. So there are two errors, right? One is the error in the field or the normalized root mean square of the state predicted by the model and the true state, and the error in energy spectrum. So here you see all these models, all the other models offer lower spectrum error than the neural operator, but the field error is subsequently, we see that field error is slightly higher. This is because when we reconstruct these high frequency components, it's not exactly phase aligned. Like the reconstructed high frequency features are not exactly phase aligned, causing a slight increase in on the field error. So this has been reported in previous studies, and we also observe a similar trend here. So if you think about it, neural operator and the adveno has the exact same architecture. The only thing different was we trained them differently. So what happens to the model parameters during adversarial training? That's what we investigated next. So we analyze the model weights. So we compare the energy of the trained weights of the neural operator and the trained weights of the adversarial NO. For reference, this is what a low pass filter looks like. It allows the low wave numbers in the kx and ky representing the wave numbers. It represents the low wave numbers to pass by, and the high pass filter is other way around. It allows the higher wave numbers to pass through. So This is the low pass filter and this is the high pass filter. And we were using a unit-based neural operator in this exercise. And let me call E1, E2, E3, E4 as the 4 encoders and D4, D3, D2, D1 as the corresponding 4 decoders. And we compute the magnitude of the Fourier transform of the learned kernels of neural operator and adversarially trained neural operator and print them side by side. So for E1, this is what it looks like. The energy of the neural operator and the energy of the adversarially trained neural operator. For E2, for E3, E4, D4, D3, D2, D1. I hope you're able to understand what I'm doing here. Corresponding to each block in the unit-based neural operator, I take the learned kernels and I compute the energy and I print them on the same scale. And if you look for all the blocks of this neural operator, we see adversarial NO behaves more closely to high-pass filter. That is, it is brighter towards the fringes, especially at the lower levels than the neural operator, the vanilla neural operator. So adversarially training the neural operator enables the neural operator to behave, neural operator kernels to behave like a high-pass kernel, facilitating transmission of information at higher wave numbers and higher frequencies. So we completed task with a super resolution. Next, we look into forecasting. Here we consider a three-dimensional homogeneous isotropic turbulence with a Taylor-Reynolds number of 90 tau, which is the sampling interval at which the states of the systems have been saved is set to 0.04. And our training data set in this case consisted just a single simulation or a single trajectory of 160 snapshots, because generating three-dimensional volumetric spatiotemporal systems using numerical methods is pretty expensive. So we tried to, and this is a problem in general suffered by all areas of science, where high fidelity simulations of time-dependent volumetric systems is expensive. So to acknowledge or reflect upon this limitation, we force ourselves to learn just from 160 snapshots of a single trajectory. So this is the load data regime. Problem setup, again, given a history of the states as the input, try to predict the future states as the output. This is the problem setup for forecasting. So in this exercise, we first compare a neural operator, an adversarially trained neural operator, and a neural operator which also penalizes the mass conservation or the incompressibility, the divergence of U. So if you look at a state 14 time steps ahead, which corresponds to like 2 eddy turnover time scales, this is what you see, the kinetic energy of the direct numerical simulation, neural operator, adversarial NO, and NO plus divergence of U. You see a better phase alignment between the DNS and the Arduino compared to NO or NO plus divergence of U. And their absolute errors are also plotted here. If you check the energy spectrum on the left, you'll see again the adversarial NO has almost perfectly aligned energy spectrum with the DNS. And the dotted magenta line corresponds to the minus 5/3 scaling, which is common in turbulent flows. Is an animation of the same, how the error evolves in time. I'm plotting the kinetic energy and their errors at the 3 mid-plane slices. And you'll see the adversarial NO is constantly having lower error than the vanilla neural operator and the neural operator that penalizes the incompressibility condition. So if you think about it, the neural operator with the incompressibility penalization achieves slightly lower field error than the vanilla neural operator. But from the last slide, you will realize that it doesn't exactly help you with the energy spectrum, because the blue line is below the yellow line. So that's what we observed. Then we also want to compare with one of the recent benchmarks called the GenCFD proposed by Molinaro, where a diffusion model is used to directly forecast the future states. So here, given the state of the system at UT and a delta t, which is the physical time step, the delta t ahead you want to predict, the GenCFD, which is essentially a diffusion model, iteratively denoises a noised state and try to estimate the state at t plus delta t. This is what it does. But the problem is estimating state at each physical time steps requires this capital T number of denoising iterations, and this becomes very expensive, especially in when you're dealing with 3D plus time systems. So we forecasted 35 time steps. It's like 5 eddy turnover time scales. And I'm visualizing a mid-plane slice of the U velocity here. The DNS on the first row. The different columns corresponds to different time steps, different time, 1, 2, 3, and up to 5 eddy turnover time scales. Second row represents the Gen CFD predictions. Third row represents the adversarial neural operator prediction. And the last row is the energy spectrum of all the states, the DNS, Gen CFD, and Arduino. And you'll see that if you look closely, the larger wave numbers are pretty accurately captured by the Gen CFD, but sorry, I mean the lower wave numbers or the low frequency modes are captured pretty well by the Gen CFD, but the high frequency component looks a bit noisy, but the adversarial NO looks more realistic. And if you look at the energy spectrum also, you'll see the green line is slightly overshooting the actual energy spectrum. It's slightly above the DNS energy spectrum. We compare the inference time here. So to forecast 35 time steps into the future, a trained adversarial neural operator took 1.97 seconds on an H100 GPU. But the Gen CFD required 228 seconds to do the same forecasting on the same GPU. So the Arduino we see in this case was 114 times faster than the Gen CFD. So one possible reasons why this could happen is in the paper they were talking about they had access to 100 to 1,000 different simulation runs to train it well. But as I said before, accessing high fidelity simulations is a big challenge and it's often not practical. So if you limit to one training trajectory, that's what we did. Gen CFD was not able to learn the high frequency modes very well, and it looks pretty noisy. Next, we compare the errors and the cost. The field errors, the energy spectrum, in which case adversarial NO achieves the lowest. We try to ensure all the models have same number of parameters or similar number of parameters. And we compare the compute cost, inference time, and the peak RAM usage. And if you look here, the compute is like an order of magnitude larger than the neural operator based surrogates. Inference time is also very large, and this is the inference time for just one time step ahead. And the compute cost reported here is just so earlier I reported the compute cost for forecasting like 35 time steps. Here is the cost for forecasting one time step ahead, and you see it's like 7.8 seconds, and the maximum RAM usage is also much larger. So the Gen CFD is indeed much more expensive than the neural operator based surrogates, but adversarial neural operator offers improved spectral representation at NO like cost. We also investigate the PQR invariance. So let me call A as the gradient of the velocity vector. So A is a tensor, gradient of U is a tensor, and this is something called the characteristic polynomial, where P is the trace of the velocity gradient minus trace of the velocity gradient, which is 0 in case of incompressible flows. Q is the minus half trace of A transpose, which is half of the norm of the rotation tensor minus the strain rate tensor. And R is the negative determinant of A. So the terminal community is often interested in the joint probability density function of Q and R. So if you look at the QR distribution of the direct numerical simulation, this is what it looks like. Like a fully developed turbulence is often characterized by this teardrop shape, and this curve called the Whaley-Fossé line, it's called the zero discriminant line. The right tail of this line has an accumulation has higher probability. If you take the PDF of Q and R, the values often tend to accumulate along the right tail of this line in homogeneous isotropic turbulence, and that's what we observe here. So classically, the physicists and fluid mechanics community is interested in the QR distribution because it tells a lot about the nature of these flows. So we decided to compare the QR distributions of the DNS with each of the states predicted. So on the left, again, we tried to, because it's a probability distribution density function or a probability distribution over Q and R, we tried to draw ISO contours at certain levels of this probability density function for DNS and overlay it with neural operator on the first curve. Adversarial neural operator in red color in the second box. Neural operator plus divergence CFU, which is the incompressibility constrained neural operator in the third box, and the Gen CFD on the fourth box. Again, you see the best alignment with the DNS QR distribution with the adversarial neural operator, followed by NO and NO plus divergence CFU, and followed by Gen CFD. Let me know if you have any questions. So we just completed super resolution and forecasting. And next, I'll go into sparse flow reconstruction. Here we consider the turbulent wake of the flow path behind the cylinder. Turbulent wake behind the cylinder, where the Reynolds number is 11,000. Again, accessing experimental or high fidelity simulation data sets is notoriously difficult. So again, to reflect upon this difficulty, we constrained ourselves to deal with just one simulation with one trajectory with 150 snapshots. Again, low data regime. So during training, we train the surrogate model to learn the probability distribution or the probability of the full flow. But during inference, we want the surrogate model to sample the full flow given the sparse measurements. So if you have sparse velocity measurement, can it accurately reconstruct the full flow field? So this is the problem statement. Why this is interesting? Because experimentally in the fluid mechanics community, you visualize flows or you understand flows using techniques like particle tracking velocimetry, in which you inject fluorescent particles into the fluid system and capture the evolution of these particles using a high frame rate, high resolution camera, and you can see how each of these particles move in time. And from that, you try to reconstruct these flow fields. And this is the problem we are trying to address. And during testing, we consider 4 test setups. Test setup 1, you are given the sparse velocity measurements all over the all over the 3-dimensional space, and you want to reconstruct the full flow field, which is the velocity as well as the pressure fields. Test setup 2, you are only given the sparse velocity measurements on a plane, and can you reconstruct the volumetric distribution of the velocity and the pressure fields. Test setup 3, you have the velocity information in a subdomain and reconstruct the full flow field. Test setup 4, can you reconstruct the pressure field when you only have the velocity information? So practically, you can measure only the velocity information correctly. So we respect that and we try to adhere by that. And subsequently, the only information provided to the model as the input was sparse velocity measurements in the subdomains in these test setups. So test setup 1, velocity in the entire domain, but sparse. Here are 2 key results. So if you have like a masking fraction of 0.5, and we try to reconstruct the flow field using the diffusion model and a GAN in this context, and you see both does a good job. But when the masking fraction is drastically reduced to 0.99, we see the GAN fails completely. This is the GAN uses a unit as its neural network backbone, and when the mask fraction is drastically reduced, like drastically increased, the distance to the nearest information point increases significantly, and units are not great at aggregating global information. So the gun fails here. Next, you have velocity only at the plane z equal to 0, and you try to visualize the state predicted at z equal to 0.25, which is not the visualized plane, but an above plane. So, of course, the diffusion model, this is the diffusion model's prediction in the middle. It is not exactly phase aligned with the DNS, but it looks statistically similar or something you could expect to see. And this is the prediction of the gun. We compare the intermittency here, which is the probability distribution function of the velocity gradient. And again, we see the diffusion model's prediction is aligned with the DNS, while the gun is not able to do it properly. It overestimates the high gradients. Test setup 3, sparse velocity in a subdomain. And this is what it looks like at z equal to 0. So you know what the velocity looks like in this small subdomain, but you don't know what is going on outside this subdomain. And the diffusion model can reconstruct the velocity well. It's not exactly phase aligned again, but it looks realistic more than the gun. And how do we quantify this? By looking at measures like intermittency again. And again, we see the neural operator, the gun overestimates the high gradients, and it totally fails in the setup. Finally, we look at the last test case where we try to reconstruct the pressure field given the sparse velocity measurement. And again, we change the mask fraction from 0.5 to 0.99. And here are the predictions. Diffusion models, pressure reconstructed, and the pressure reconstructed by the gun. And you will see a better alignment between the diffusion model and the DNS compared to gun. So in conclusion, we identified 3 practical problems where vanilla neural operators fail. We found the reason for the failure is spectral bias, and the remedy is utilizing or leveraging generative models. For the super resolution, spatiotemporal super resolution, adversarial neural operator work best in terms of the cost and the error trade-off. For forecasting also, adversarial neural operator worked best, and we compared it against a physics-informed variant and a diffusion model-based variant. But in the sparse flow reconstruction, adversarial training didn't really help. We had to use a diffusion model to make this work. And in the future, we could look at applying these methodologies to other multi-scale systems like compression and reactive flows, fusion plasma in the modeling of tokamaks, then magnetohydrodynamics and weather modeling. We can investigate how it can be used to accelerating LDS or DNS. And we can also try investigating how these methods can be generalized to unseen geometries or flow conditions. These are my collaborators who helped me a lot to get this work done, and I'm grateful to them, and I'm thankful to my advisor, Professor George Kaniadakis. I also acknowledge the help from Dr. Jen Zhang, Professor Martin Maxey, and Dr. Johannes Brandstetter. And I also acknowledge the funding resources. These are the references, and thank you. I am happy to take any questions.
Thank you so much for your great talk. Do we have any questions for the speaker? Yes, Ahmed.
Oh, yeah. So thank you. Very great talk. And
Thank
so
you.
regarding the neural operator and then the adversarial loss function, did you
Yes.
other neural operator than unit like DeepNet?
We actually tried. So we tried DeepNet and Fourier neural operators, but it did not work. The DeepNet, the problem was when we tried training a DeepNet to learn the impinging jet case, it just couldn't learn at all. Even the low wave numbers, it couldn't learn accurately. So you need the neural operator to get at least the halfway through, or some part it needs to be done. That's what we observed. For the Fourier neural operator, when we tried, it was in general unstable to these high frequencies. And once we introduced the adversarial training, it started blowing up and we were getting nines. That's what we observed. So we observed like unit-based or convolution-based neural operators would probably work in this context. But thank you for the question.
But if you use like convolution layers in the deep neural in the branch net, for example.
Yes, that's
that
what
we-
we did. Like we used the
Oh, okay.
convolutional neural network for the branch net and MLP for the trunk net, then did the basis reduction, like projected using the learned basis learned by the trunk net. And it could not really learn the evolution of the system in time very well. So that even adversarial training couldn't help it further. So that is what we observed.
Okay, thank you.
Thank you very much for your question.
Do we have any other questions? I have one question. Other than MLP, did you try the Kolmogorov-Arnold network or any?
No, I did
like
not.
with-
No.
Okay.
Like you meant for the trunk net of the depot net, right?
Yeah.
No, I did not. I didn't try depot kinds, no.
Okay. Because I'm currently working on a architecture of Kolmogorov-Arnold network that can get rid of a spectral bias. But I wanted to see like how it works on your problem, because I'm not working on this kind of problem.
Yeah, I felt like when you have space and time involved with multiple scales, like these slow energy decaying systems with space and time, then things start getting a lot more challenging because you need a global basis function. So I assume you would be taking X, Y, and T as the input to the trunk network, whether it is an MLP or the Kolmogorov-Arnold network. Then you need to get like a global basis for all the states you are going to encounter in this system. So as these dimensionality increase, I know theoretically you can say just start using wider networks or deeper networks. You can say that, but then even theoretically they say like it increases the greediness for these systems. So especially when you go to like 3D states, accessing three-dimensional time-dependent systems is very notoriously difficult. So you need to make it work in the low data regime. So I'm not sure if that would be very helpful, but it's definitely worth pursuing it.
Yeah.
Thank you for the question.
Yeah, I saw Chianing has a question, right?
Yeah. Yes, I have a question. Great
Yes,
talk,
Chen.
Vivek. Could you go back
Thank
to
you.
the slide with the loss function?
Yes.
Yeah, yes, here. Compared to the loss function of the neural operator, the serial neural operator add three more terms, right?
Yes, it has three more terms. Yes.
Yeah. Have you investigate which term play most important role in improving the results?
Yes, the main term the term that played most important role is this LG, which is we are trying to pull the discriminator, like we update the neural operators parameters such that the discriminator is not able to distinguish which is neural operator prediction, which is the true state, which is the actual state. So I felt this is the most important term, but we also use this because in the computer vision community, they have shown this is called the perceptual loss term, which highlights the high frequencies or the different frequencies. So this has been a common practice, but at least in our experiments, we observed like the LG, this third term was the most important term.
Okay. Could you explain more about the second term? What does phi means?
Yes.
The phi means
so,
frequent.
So the phi means so you have a pre-trained network. So in this case, let's consider in our 2D cases, we took a pre-trained VGG net, VGG19 net, that is a large convolutional network that was already trained on large datasets, ImageNet datasets. So since these networks were already exposed to these data, it already learned to extract some key features. So let us say it has like 10 or 20 convolution layers. We took the first 5 convolution layers of the VGG net, send the neural operators prediction as the input to the VGG net. So it has the output of the first layer, second layer up to 5th layer. So these are the true phi. So this corresponds to the phi L of U target. So you give the U target or the true solution as the input to the VGGNet, extract the state at the intermediate levels, and you have phi L U tar or the U target at the Lth level. And you do the same thing with the neural operators prediction. Phi L
Okay.
at given the neural operators UF as the input. Neural operator prediction UF as the input. And now you minimize them weighted by weight WY. So we were following, there's something called real ESR GAN. We were following their methodology. And but instead of training a separate generator, we just adversarially train the neural operator, which is a time conditioned unit in our case.
Okay. Okay. Thank you. Get it.
Yeah. Thank you for the question. Yeah.
Thank you. Do we have any other question? Do you want to add anything to your presentation? Since we still have time and our second speaker will be here only like at 1 p.m., right?
Right. That's true. I'm open to more questions. I'm happy to answer more questions if you have any more questions. You can ask me anything. So yeah, the key is making things work in the low data regime, continuing to the question Nazrin asked. So that is one thing. And yeah, following up on what Jianing asked, for the 3D case, we use a pre-trained network that is trained on MRI images of human organs, so that we could get some perceptual from a pre-trained network on large data sets that has the volumetric nature while they were originally trained. So yeah, that is what we did for the 3D case. And for the the point of what I'm trying to make is like, I'm not saying adversarially training in neural operators is always beneficial. Depends on the problem. For some tasks it helps, but for some tasks it really didn't help. So we should keep exploring. And of course, the spectral bias of minimizing an L2 based error is definitely a problem, irrespective of what. But in applications where you don't care about the fine details, then you could as well go ahead with the neural operator. Because if you look at any of these, since these energy spectrums are in the log scale, even the neural operator captures well up to 10 power minus. It's like more than 99% is already captured by the neural operator, even in this case. So yeah, when you want the smaller details, then you might want to resort to this.
Yeah. Yes, Max has a question.
Yes. Hello,
Hi,
Vivek.
Max.
Hello
Hi,
to the
Max.
rest
Hi.
of the group. Nice to see you guys.
Nice to see you, Max.
Very nice talk.
Thank you.
I have a question to the last part of it.
Yes.
So where you compare the different test cases, did you also try PINNs on that or something with physics-informed losses? And can you comment
Yes.
on how much that could help in this scenario?
Right. So for the forecasting case, we compared with a neural operator where we penalize the divergence of U. So the problem is we simulate the homogeneous isotropic turbulence in this case with a direct numerical simulation. So the simulation has a numerical delta t, which is very small. But typically, we don't save the sampling interval, which is the delta t at which you save the states, is much larger than the numerical delta t that ensures stability of the scheme. All right.
Mm-hmm.
So we could not therefore enforce the momentum conservation, but we could still enforce mass conservation, because to enforce mass conservation, all you need is one snapshot, which is a volumetric snapshot in this case. So here, the second column is the Van Laan neural operator that minimizes the, let's say, MSE of the true and the predicted states. NO plus divergence U minimizes the data as well as the divergence of the predicted velocity fields, which is ux plus vy plus wz, where the subscript represents the derivative. So that should be 0. So that's what we did. And what we observed was, just a second, having the physics informed loss helped bring down the error or the field error. By field error, I mean the true UVWP minus predicted UVWP and MSE of these things, or normalized root mean square error of this. So that helped slightly reduce the field error. But if you look at the error in the energy spectrum, it's actually slightly below neural operator. Like the energy spectrum error is slightly larger than that of the neural operator. So that's what we observed. Does that answer your question, Max?
Yes, somewhat. I mean, these are interesting results. I wonder why it makes the spectrum worse. Do you have any idea?
Yes. So my understanding is if you take the divergence of the velocity field as well. So how do you minimize, what is the physics informed loss? It's typically an L2 error, L2 norm of the PD residual, right? So the divergence of U also has this small scale details, and you're again trying to minimize like the L2 norm of the PD residuals, which has the small scale details. So again, that also suffers from spectral bias. So, so the large scale details of the PD residual is indeed utilized by the NO plus divergence of U, which is probably why you are seeing lower errors in the field errors like UVW minus UVW pred. But the energy spectrum, not really. It's another term that contributes to the spectral bias.
Right. Okay, that's interesting.
That is my interpretation. Question. Okay, thanks. That's a deep question. Thanks.
Yeah, I think we observed something similar. So I was wondering.
Okay, cool.
Yeah,
that's cool.
Maybe a follow up to the
yes, please.
Flow field reconstruction from sparse measurements, since we also tried something like that. I mean, you motivated it with PTV measurements. We actually tried to do something with PIV measurements and try to reconstruct 3D flow from a 2D slice of measurements. But so far that didn't work that well. We approach it with pins and variants of pins, so not only vanilla pins. But yeah, it looks like you get better results with diffusion model, right? Did you compare to pins?
No, we did not compare it with pins here as well. No, here we just compared with a GAN and a diffusion model. Here so the thing is here we didn't super resolve flow reconstruct in time. We just had independent snapshots. So we just used a GAN and a diffusion model. We did not compare with pins.
Okay, I see. I mean, it's interesting to see that diffusion models perform well there. So might try that out.
Right. The thing of the advantage of diffusion model is like, given a new, you train it once, now you give a new input, you don't have to retrain it again. It just iteratively denoises and infers. Like one inference typically takes like 10 seconds at most. That's it. But the classical pins requires retraining for every new thing. So you need to come in somewhere in between. So that's what I understand.
Okay, nice. Thank you.
Yeah. Thank you. Thanks for the question, Max.
Of course.
Okay. Do we have any other question? If not, I think it's time to move to our second talk. Thank you so much, Vivek, for the presentation. Yeah. Brandon, can you hear me?
Hi, yes, I can hear you.
Hi, great. Can you share your screen to see everything works?
Can you see?
Not yet. Yes. And can you put it on presentation mode? Yes. Great.
Might just
Wait. I have to introduce you. Our second speaker is Brandon Yee. He will be giving a talk on meta learning pins for few-shot parameter inference. Brandon Yee is a high school senior at Weston High School, and he is a principal investigator at Independent High School Research Group YCRG Labs. With that short introduction, the floor is yours, and you can start your presentation. And we can't wait to hear about your work.
Thank you for having me. So I'm going to be presenting on meta-learning physics-informed neural networks for few-shot parameter inference. So this is a table of contents for my slides: problem solution, methodology, results, limitation, future works, discussion, and then the Q&A. So last year, at the end of my senior year, I started exploring PINNs in my physics 1 class, right? And so I was started with modeling the Navier-Stokes equation, right? And I found that for each different Reynolds number, I had to retrain my model, right? So the key problem was traditional approach required retraining for each model, and that was roughly 500 steps. And there was no leverage of the shared fluid dynamics principles that come from like NSE and also just general physics. And so each model had to relearn how to do these things. And so traditional machine learning requires millions and thousands of labeled data, and it cannot transfer the problem information, right? And then this is also the same in PIML, where each problem is solved independently from scratch, and it only generally transfers their like core principles, which is like the physics informed part. But physics few-shot learning allows you to train from multiple related tasks, and it extracts the transferable patterns. So like between the Navier-Stokes equations, the similarities and the of how they're modeled, right? You can extract that knowledge, and it can only and it can train under very low examples because it takes the information and its past learnings. So thing is, even though we don't model it this way, physics problems share these structures, right? They share the governing equations, conservation laws, physics constraints, right? And so there's similar governing equations, and then there's also similar parameter to observation relationships, right? And thus there's transferable inference patterns between these different physics scenarios. So between different types of modeling and fluid dynamics, you can meta train across multiple related physics problems with the known parameters, right? And then rapidly adapt the model to new parameter regimes with the learned data, and you only need not that much because you have the knowledge from the learned patterns. So I'll start the formalization. So we consider a distribution over physics has P of t, where each test Ti is characterized by a domain omega I, right? Which is a subset of Rd with boundary partial omega I. And then for the governing equation, Fi of ui x equals 0 for x and omega I. And then the boundary conditions are Bi of ui x equals 0 for x and partial omega I. And the limited trading data is Di equals the set of data points xj, xj uj for j equals 1 to ni, where ni is some small amount of data. And so the shared structure enabling knowledge transfer comes from the common PD forms f across tasks, right? So like Navier-Stokes family, and the similar boundary condition types B within the physics domains, and the transferable solution patterns between related parameter regimes. So our meta learning goal is a meta model enabling quick adaptation to new tasks using prior knowledge, and then plus any minimal data plus physics constraints. So we're extending the model agnostic meta learning, right, to transfer physics knowledge across tasks. The meta objective learns transferable physics and inference strategies, right? So theta star equals argument over theta expectation over t sampled from P of t of L total of phi t and t. And for fast adaptation, we apply the learn strategy to new physics tasks. Phi t equals theta minus alpha times gradient of theta L total of theta and t. And the total loss combines data fitting with physics knowledge transfer. L total of phi and t equals L data of phi and t plus lambda t times L physics of phi and t. And the key innovation here is the dual optimization. The inner loop enforces the physics constraints during task-specific adaptation, and the outer loop trains the transferable patterns across physics tasks. So we're combining rapid adaptation with physics consistency, and the knowledge transfer happens because the data captures the shared physics infrastructure strategies. And so for the physics loss implementation, the physics loss leverages common PE structures across tasks. So L physics of phi and t equals expectation over x sampled from omega f of of u phi at x squared plus exploitation over x sampled from partial omega b of u phi at x squared. And for interior constraint enforcement, the PD residual must be 0 throughout domain omega. So the shared equation form F enables knowledge transfer across the common tasks, and then the common physics patterns are learned from the multiple related problems. So for boundary constraint enforcement, boundary conditions B must be satisfied on partial omega. Similar boundary types within physics domains enable transfer, and then the boundary handling strategies are learned across the different task distribution. And the implementation uses automatic differentiation for consistent derivative computation across tasks, and then collocation sampling for standardized expectation approximation. And the transferable physics patterns for the same constraint evaluation across the related problems. And the key insight is that consistent physics constraint enforcement creates a shared learning signal that enables knowledge transfer between the related physics tasks. And then this is the adaptive constraint weighting, where different physics problems need different balances between data fitting and physics constraints. So we learn the task-specific physics importance through an adaptive weighting mechanism. Lambda of t equals sigma of w lambda times ht plus speed lambda. And the text embedding ht captures problem-specific features through a learned encoding that extracts transferable task representations, and cross-task patterns enable optimal weighting strategies, and the domain expertise gets embedded in the learned parameters w lambda and b lambda. So for the adaptive learning, ht equals task encoder of geometry, physics complexity, and like data quality. So this accounts for different geometry variations, like different domain shapes and boundaries, and the physics complexity includes including equation stiffness, right? And equation stiffness, nonlinearity, and also like multi-scale effects and data quality covered different noise levels, sparsity platforms, and measurement locations. And so knowledge transfer benefits include optimal balance between data fitting and physics constraints per task type. So the learned weighting strategy that transfers across the related problems. It also includes task-aware adaptation that automatically adjusts to problem characteristics, and meta-learned expertise that captures physics intuition about constraint importance. And so then we provide mathematical analysis of the knowledge transfer framework. The convergence rate with physics knowledge transfer is expectation of gradient L at theta t squared is less than or equal to c 1 over t plus c times 2 times squared root of log t over t, right? And this analysis works under standard assumptions. The loss function L Lipschitz continuous with L less than or equal to c1. And then the gradient variance is bounded by sigma squared less than or equal to sigma 2, and the physics constraints are Mu strongly convex and constraint-based. The constraints reflect knowledge transfer benefits. So C1 equals L data squared plus lambda squared, L physics squared over mu, and C2 equals lambda squared sigma physics squared. And so the data term L data squared comes from the standard meta-learning convergence, and then the physics term lambda squared L physics squared over mu shows constraint regularization effect, and the strong convexity mu large accelerates convergence through the different physics knowledge. And the key insight is that the physics regularization lambda large improves rates when constraints are informative. So when they like tell a lot, and then the well-posed physics mu large provides better conditioning via shared structures and cross-task patterns in physics enable the faster convergence than the independent learning. And so the sample complexity analysis. So for theoretical sample efficiency, our sample complexity bound for physics instrumental learning is n equals big O of d log of 1 delta over epsilon squared times 1 plus gamma. And so comparing with standard approaches, standard meta learning complexity is big O of d log 1 over delta 1 epsilon squared samples required, right? And so our physics informed improvement gives a factor of 1 plus gamma reduction, where gamma is greater than 0. And the knowledge transfer benefit is that gamma quantifies how much physics constraint reduced the sample requirements. So the effective dimension D represents problem complexity and after physical regularization. The physics regularization impact depends on constraint strength, and then gamma equals F of lambda mu and constraint quality. Constraint strength lambda increases gamma, indicating stronger physics knowledge, and then the convexity parameter mu improves gamma for well-posed physics problems. And so better physics knowledge leads to exponentially fewer samples required. The key is that transferring physics knowledge across tasks provably reduces sample complexity compared to learning each task separately and independently. And so this is our experimental setup. We did comprehensive evaluation of fluid dynamics. Problem classes include the Navier-Stokes equations, round numbers 100 to 1,000, heat transfer with varying boundary conditions, Berger's equations with varying viscosity, and then lid-driven cavity problems with varying geometries. The data set structure include 200 training tasks, 50 tasks per problem class, 20 to 100 data points per task for adaptation, and then creating realistic few-shot scenarios for computational physics. The analysis framework uses level alpha equals 0.05 with Bonferroni correction. Effect size is calculated using Cohen's d, and then power analysis with beta equals 0.8 for sample size calculations. Statistical tests include the two-tailed t-tests for group comparisons and ANOVA with post hoc 2K tests where appropriate. So this covers diverse fluid dynamics phenomena to test generalization, and then Reynolds number variation tests robustness to parameter changes. Each PUM class represents different physics complexity, and then small adaptation data sets simulate realistic engineering scenarios. So comprehensive evaluation ensures like all the results are specific around problem. And you can see we had from the statistical test, we had relatively normal accuracy results. And so our main results are you can see our models compared to others in terms of validation accuracy comparison on these low data sets, right? So we had 92.2% validation accuracy, which beats both the transfer PINN, which is transfer learning over different pins, which is 0.824, and then there's the standard PINN training over trained on one and then evaluating over different models, which is 0.783. And then so there's a 15% improvement in generalization performance. And you can also see 3x fewer adaptation steps compared to when you go to the next problem. So standard PINN is retraining every time. Transfer PINN is less mammal. This is just pure meta learning. That's 100. And then reptile and multitask, there are other benchmarks that were varying amounts. But as you can see, ours is 50. And so these results show both statistical and practical significance. The 15% improvement is substantial in computational physics applications. 3x reduction in adaptation steps is critical for all those real-time applications. And then the large effect size means that the difference likely matters in practice. And confidence intervals show the robustness across the different performance tests. And so this is just another show of our results where we can see consistent improvement across all few-shot settings, and the performance gap increases with more adaptation data. So the standard deviations are smaller for our method, indicating there's also more stable performance, and we achieve substantial improvement even in very few-shot scenarios. And so the convergence analysis, the physics constraints accelerating meta learning. Convergence benefits include faster convergence with physics constraints, lower final loss compared to standard mammal, and better conditioning of optimization landscapes, and stable training across different initializations. The conversion comparisons during the meta training shows our physics-informed meta learning approach converges faster and achieves lower final loss compared to standard model agnostic meta learning and transfer learning PINNs and standard PINNs. The physics constraints provide better conditioning of optimization landscapes, leading to improved convergence properties. And this essentially demonstrates that the physics constraints provide inductive biases that guides optimization. So better conditioning reduces sensitivity to hyperparameters, and the practical benefit is shorter training times for the meta learning phase. And physics knowledge helps you avoid the poor local minima. And so then this is our allocation study. You can see each component contributes significantly to the overall performance. And each point provides a different configuration plotted as validation accuracy versus adaptation efficiency measured by the number of steps required. And the full PI mammal model achieves the best trade-off between validation accuracy and adaptation efficiency, and the lower right is better. And removing any component degrades performance. So the systematic evaluation validates each design choice pretty much, right? And the physics constraints are the most critical component, and they validate our core hypothesis that like this is usable. Then the meta learning framework provides like these substantial benefits over transfer learning could, and all p-values indicate the statistical performance. And so in computational efficiency, we see significant computational savings. Time drops from 12.4 hours for standard PINNs to 4.1 for our PI mammal, and memory usage decreases from 8.9 gigabytes to 5.9 gigabytes. GPU utilization also increases from 85 to 88%, and energy consumption drops from 24.8 to 8.2 kilowatt hours. So this represents a 3x reduction in training time compared to the standard PINN, 67% reduction in training time and 67% reduction in energy consumption, and lower memory requirements enable larger problem sizes. So higher GPU utilization also indicates better computational efficiency. So these energy savings are important for application requirements, and the efficiency gains are also important for like actual deployment. And so it shows that these computational benefits are make the approach practical for real world benefits where computational resources are limited. And so the current constraints is I really only tested on fluid dynamics. So I would like to expand to broader fluid dynamics. So and then the parameter ranges are also only Reynolds numbers, limited to tested Reynolds numbers geometries for validation. And then the scalability, I haven't really scaled it to high dimensional problems, so there isn't a lot there to talk about. Technical constraints include the regularity assumptions and theoretical analysis, smoothness requirements for automatic differentiation, and collocation. Sampling may miss some important physics features. And then the mathematical framework constraints mean convergence analysis assumes Lipschitz continuity of loss functions, which the bounded gradient variance across task distribution and strong complexity of physics constraints and the standard regularity conditions for meta learning. And so the practical considerations, even though it's 94% accuracy, this might miss subtle effects, and adaptive weighting requires task embedding quality and the finite sample effects in finite and in few-shot parameters. So it's important. Essentially, the model is only specific to fluid dynamics and needs validation in other domains. And the theoretical analysis assumes standard Burr-stick assumptions, and the real physics problems might violate some regularity conditions. And these are areas for continued research, so leaning into continued research. So future research directions include domain expansion, where I want to also do stress-strain relationships, electromagnetics with Maxwell's equations, and quantum mechanics with Schrodinger's equations, and multi-physics coupled problems. The methodological improvements include hierarchical meta-learning for multi-scale problems, symbolic AI integration for enhanced physics discovery, and uncertainty quantification in meta-learned representations, and active learning for optimal data and collection strategies. So theoretical improvements include non-convex physics constraints analysis, distribution shift robustness guarantees, multitask learning bounds for physics problems, and approximation theory for neural PDE solutions. And the algorithmic advances I can make include second-order meta-learning, faster convergence, gradient-free optimization for non-differentiable physics, federated learning for distributed physics computation, and continual learning for evolving physics understanding. And so this represents a natural extension to other PDE-based physics domains. Each domain brings unique challenges and constraints, which could be interesting for testing my model. And the hierarchical approaches could handle multiple physics scales. And the symbolic AI could help improve interpretability and discovery accuracy. So current theory also assumes complex constraints. We need non-convex analysis, and the second-order methods could improve convergence rates. Sorry, I went really fast. I'm very nervous. Yeah, that's my presentation. Thank you.
Thank you so much. Do we have any questions for the speaker? Yeah. Vivek.
Hi, Brandon. Nice talk.
Thank you.
Can you go to the methodology again? I didn't fully get it, I guess. The methods section. So you have multiple flow cases. So during training, what all cases are you exposing your model to? Can you tell that one more time?
I'm sorry, I couldn't hear your question. Can you say it again?
Yes. So during the training of your PI-MAML, what all Reynolds number did you consider?
We're considering 100 through 1,000. So Reynolds numbers between those. And those are mostly incrementing by 100. But we also incremented by 50, and we had variation.
All right. And compared, okay, can you go to one of your results where you compare with standard pins?
Here.
Yep. So my question is, how was the training different for the standard pin and PIAML?
So we trained it essentially over the different scenarios, right? So for the standard pin, it would have to retrain every time. It didn't share that continual knowledge. For the PIML, we trained it over the problems over and over again, or on the different problems, right? So it was able to adapt for a different problem. But for the standard pin, it can't do that because it doesn't have the shared knowledge per problem.
What if you just gave, if the change in the problem setup can be shown by a single parameter like a Reynolds number in this case? What if you gave Reynolds number as an additional parameter? I know it wouldn't work as good as the PIMAML, but just to ensure a fair comparison training.
We had when we gave it as a parameter, it had for the pin, because it generally because they require extensive data because they're not doing few-shot parameter inference, right? For the larger amount of data, it would overfit to each pin, and then as you change the parameters, it would the model would vary too much.
Understood. All right. Okay. Thank you. Great talk, Brian. Thank you.
Thank you.
Do we have any other questions for the speaker? I don't see any other questions.
Well, I might have.
Yes, Sasha.
Hi, Brandon. Great talk. Thank you. My name is Sasha. I'm a postdoc with the Crunch Group. I was wondering, can you have a word or two about how your approach to meta learning compares to other ways of meta learning that are out there in terms of advantages, but also in terms of disadvantages?
So our approach is that we also take the physics constraints. So meta learning hasn't really been used in physics-informed machine learning before, right? So our model uses the physics constraints combined with the past learnings that meta learning uses in other fields for machine learning. And so that allows us to have just a better understanding of the problem when we're testing.
All right, thank you. And maybe a second question. I'm actually not sure whether you mentioned the talk, but I've been looking through the paper that you put on GitHub in parallel, and you're mentioning there the discovery of causality, and I didn't quite understand how you do that, how you are sure that these are causal relationships that you're discovering.
We weren't necessarily, that was just a manuscript that but essentially we weren't necessarily sure, that's why I didn't include it in the thing, but it was the relationships that it was determining. And then for some of the other relationships, we could validate them because we validated them against the tested round numbers with like the standard pin.
All right, thank you very much.
Thank you. Do we have any other questions?
And then one more question. Can you comment on the training costs for each of these models? I understand pins would be less for sure because it's trained only on one of the scenarios, right? So it requires a full retraining for a new scenario. But what about, let's say, multitask learning and PIMAML, the training costs?
So in terms of training costs, that's shown in terms of steps, right? They're just asking about how the computational
pre-training.
Huh?
The first training, the pre-training, before you adapt it to the specific case using a few examples there. You did some kind of global training initially, right?
Yeah, they're all trained on the same thing. And then they're continuing
Okay.
to, like, the transfer PINN is transfer learn to other problems. And then the standard manual is also does the same thing as our model. It just doesn't have the physics form parameters. And then Reptile and
Okay.
Multitask also do their they all have some sort of informed relearning, but the standard PNN is the only one that's training fully from scratch.
Understood. All right. Thank you.
Thank you for your question.
Do we have any other comments to add? I think we will not get any more questions. Thank you so much for your time and
Thank
joining
you.
us today and your great presentation. And thank you everybody for being here today. Have a great weekend.
Have a good one.
Great talk.
Thank you.
Bye.